Okay, this is 8.7 coordinate proofs with quadrilaterals. The main thing I want you guys to be able to do is be able to figure out missing coordinates. So the objective, students will be able to name coordinates of special figures by using their properties and prove theorems using coordinate proofs. Okay. In the diagram to the right, rectangle ABCD is centered at the origin. Okay, so right away we know some things. We know that this is a rectangle. Alright, and it's centered at the origin. And it says the sides are parallel to the axis. So these two sides are parallel with the x-axis, and these two sides are parallel with the y-axis. That tells us some things. That tells us that this distance here from the axis, since it's in the center, has to be the same distance as this. Well, this coordinate here, let's zoom in. This coordinate here is a comma b, meaning that this distance here is, this is a, and this height is b. Well, that means that this is a, and this is b, and this is a, and this is b, and this is b, and this is a. But when we talk about coordinates, remember that kind of gives us direction too. So this isn't a positive a anymore because now we're going back. So now this would be negative a comma b. And down the bottom right here, this would stay a positive a because we're still to the right, but now it's a negative b. And then in the bottom left, they're both negative. So just be negative a, negative b. And that's it. We found the missing coordinates. Okay. I'm going to kind of do all of these with you guys for practice number 2. It says place the following figures on the coordinate plane with all the vertices labeled square. So we'll do a square, we'll do a parallelogram, we'll do an isosceles trapezoid, and we'll do a rhombus. RH for rhombus. So this is how we're going to do it. Let's just zoom in and let's just draw ourselves a square. And let's put one of our vertices right there on the axis, because that way I have one of them. It's really easy to find, 0, 0. Well, what's the sides of our square going to be? We don't really know, right? So let's just say that all the sides are a. Alright, well if this distance here is a, that would make this coordinate a, 0. And then this distance up and down is also a, that would make this coordinate 0, a. And if it's a up and down and a left or right, that would make this coordinate a, a. And there we go. We have ourselves a square. How about a parallelogram? Well, let's draw a parallelogram as well. It doesn't have to fit on the little grid that you have there. Again, I'm going to put one, get a freebie by just putting that one on the origin. And if I could say that maybe this top and this bottom are both a, that would mean that this corner down here, this is a, 0, because we didn't go up at all. But we went to the right, a units. Well, this left and right, a units, doesn't have anything to do with how high this is or how far over this is. In fact, we don't know either of those. So we're going to have to use two completely different coordinates. We'd say b, comma, c, making this b and making this c. Alright, well this top part is still a, so if I went over b units to get to here and then another a units to get to here, doesn't that mean I went over b plus a units? So I would say that the x-coordinate is b plus a, and then the height is still c. That's it. Alright, so there's the parallelogram. Let's do the isosceles trapezoid. And actually for these next two, I would say you should probably pause the video and just try these and then watch the video and see if yours still makes sense with what I do. That's probably a good idea, but I'm going to go ahead and just crank them out. So here's the isosceles trapezoid. Again, I'm just going to draw it. Alright, and I know that these two things are the same. Now that tells me something that maybe you're not quite, you didn't pick up on maybe right away, but if those two sides are the same, that means that this distance and this distance here are going to be the same. So let's call this B and let's call this B. And then let's call this top side, let's call that A. Alright, well that gives me quite a bit of information here because I may not know this height, but I can call this point BC, and then I could call this point B plus A comma C, because the height's going to stay the same. And then down here, if you think about it, how far over did I go? Well, I went over B plus an A plus another B. So we could say that point is 2B plus A comma C. Instead of just using a whole new coordinate there, I'm using ones that I've already used. And now let's go to the rhombus. And you're going to look at the rhombus and you're going to realize it's very similar to the parallelogram. So let's take a look. Let's draw the rhombus. Remember, all the sides are the same. Let's say that they're all A. A, we just usually start with A just because, you know, it's the first letter in the alphabet. So this is A0. And now we're kind of stuck because we don't really know how far over this rhombus is, because this rhombus is going, I mean, the way we drew it is going up and down like this, right? But it could be going like this or like this. So we don't really know where it's at. All we know, maybe if we were to draw a little right triangle here, I mean, we would know that the hypotenuse is A, but that doesn't really tell us much about this height here, about this coordinate, I mean. So we're going to just pick two new terms. We're going to call it B comma C for this point, and that would make this point B plus A comma C. And if you look, that's almost identical to the parallelogram. And I am going to do something here that I didn't do in class. We could kind of make a formula here, and you might get kind of confused because I'm using A, B, and C, and those are the same things we use for Pythagorean theorem, except for things are kind of mixed around now. Because when we say that this is BC, we're saying this is side B, this is side C, and then this is side A. So we got ourselves a little right triangle here. And if we really wanted to figure out what A is, we could probably figure something out in terms of B and C that make these things related. So we could probably figure some terms out for B and for C that uses just one of these two variables instead of brand new variables. So let's try and do something for C, okay? Let's try and solve for C. And this is just something we can do that's just kind of fun. We could say that A squared in this situation would have to equal B squared plus C squared. And if we wanted to solve for C, we would say A squared minus B squared equals C squared. And then we could take the square root of both sides, and we could say that C is actually the square root of A squared minus B squared. And then we could actually take that and we could plug that in for our C here and for our C here. Now this is extra, this is one we need to know, but just showing you how we could use coordinate geometry to simplify this even more. And so we could have this rhombus drawn out in just terms of A and B. You know, and we would know quite a bit about it using just terms of A and B. So just something to think about, something to add, but I broke it down and added this third variable C just to make things a little bit simpler. Okay, let's go to the next page. Alright, this one is one I think you guys should be able to do on your own. I'm going to let you try it, so I would recommend that you pause the video now and just give it a shot on your own. It says use the properties of a parallelogram ABCD to find the missing coordinates. And here's the missing coordinates here. So I'd go ahead and pause, give it a try, and then come back. Okay, hopefully you tried it on your own. A couple things to note here. This is definitely an S, not a 5. So this is S comma 0 down here, which means that this distance is S, which means that this distance is S. And if we had a distance of B here and a height of C, over here we would still have a height of C. And here we would have a distance of B plus S. And those would be our missing coordinates. Like I said, I thought you guys should be able to do that. Hopefully that's what you got. Okay, this is the last one. This is a coordinate proof. And these are the things that people got the most confused on before. So let's spend some time really talking about this. It says place the square on the coordinate plane. Now we could place this square anywhere. We could go here, we could go here, we could go here, go here. But since I'm going to be dealing with the midpoints, the easiest way is to draw this square centered at the origin. So let's do that. And then let's label all the vertices. Well, this would just be a positive A, And we could say that this is, oh, by the way, that means that this is a distance of A, and this is a distance of A. And so this would be A, negative A, and this would be negative A, and this is going to be negative A, positive A. All right, the reason why I wanted it like that is because since I'm dealing with the midpoints, now I have midpoints that are really easy to find. Look, they're right there on the axes, and I don't have to work really hard to find them. So that's how I'm going to label my midpoints, which are M, N, P, and Q. They wanted me to label those my midpoints, and then we're going to write a coordinate proof to prove that this square, this quadrilateral that we just made by connecting M, N, P, and Q is in fact a square. The midpoints, when you connect the midpoints of a square, that it makes another square. We want to prove that. Okay. Well, let's find the coordinates first. M here would be negative A, 0. N would be 0, negative A. P would be A, comma 0. And Q would be 0A. All right, in order to prove that something is a square, there's two things we need to check for. We need to do a rectangle check, and we need to do a rhombus check, and it needs to pass both of those checks. So let's do the rectangle check first. The way we check to see if something is a rectangle is we prove that the diagonals are congruent. Well, in this shape, we have diagonals MP and QN. So let's find the distance of each of those. Well, MP. I should be using blue here. All right, MP, if we look at it, if this is at A0 and this is at, if this is at negative A0 and this is at A0, that means that this is a distance of A and this is a distance of A. So this total distance is 2A. All right, the other diagonal is QN. And we're going to see that it's the same thing. Look, if this coordinate is 0, positive A, and this is 0, negative A, that means that we went up A and down A. So A and A, another 2A. So we could say the diagonals are congruent because they both equal 2A. So it is a rectangle. All right, let's do the rhombus check now. Now the rhombus check, we need to prove that these things are perpendicular. Okay, we need to prove that this and this are perpendicular. Now this is actually a little bit easier because we chose to do to place it where we did. We actually have the diagonals already drawn, right, with the axes, and we see that, hey, QN is the is equal to the, or we could just say is how would we just say is on the y-axis, and MP is on the x-axis. Therefore, it's just a known fact that QN, or that the y-axis and the x-axis are perpendicular. So we could say, therefore, QN is perpendicular. That's a perpendicular symbol to MP. So it is a rhombus. And if it is both a rhombus and a rectangle, then we have proven that it is a square. And you probably don't want to write that over top like that. You probably want to write that on the bottom. I just do that for fun. But you could say, since it is a rectangle and a rhombus, it is a square. And that's it. All right. See you guys next chapter.